Good morning. I'm Matteo Massironi from the University of Padua. Together with Angelo, Riccardo, and many others that have an important part here during this course. We set up this course, this winter's course 4 years ago. And I am happy to share with you my experience, some of my knowledge about small bodies that has been part of my study through planetary geology. Today I will talk about, in particular, the geological and geostructural mapping of some small bodies, with particular regard to Comet 67P and even Phobos, which is actually moon, but has a dimension of a classical small body. So starting with the definition, here are the smaller bodies that has been visited so far from explorations, satellite orbital exploration that you see here. You see that they have different dimension from some 100 meters to kilometers. Among these small bodies, actually, there are two classes, the comets and the asteroids. The asteroids, you have seen already some asteroids that are so big, 500 kilometers, for example, Vesta, 1,000 kilometers for Ceres, or more or less, that are so big that could be considered small, very small planets, if you want, even if they are still asteroids in the asteroid belt. So the asteroids are made up of rocky material mainly, with some iron, eventually quantities, and a few quantities organics and volatiles. They have an elliptical orbital, and mainly most of them are in the asteroid belt, but we will see where they come from. And the comets actually are icy body, but contain organics normally, a lot of organics, and can contain silicate dust and some rocky material. So they are, in some cases, some asteroids become, after impacts, comets, if you want, or at least active asteroids, sublimating asteroids, because when you expose volatile materials, so ices, to the sun irradiation, you have the sublimation. So we can start with the asteroids. The asteroids are the source of the asteroids, as I said before. Most of them are from the asteroid belt, which is a belt between 2 and more or less 3.5 astronomical unit from the sun, so from 2 to 3 times the distance between the Earth and the sun, and most of them are in these asteroid belts. We have seen already Vesta, that it's there, and many other. There are some other that are injected within the inner solar system, and they have orbital movements that intersects the orbits of the terrestrial planets, like Ryugu, for example, or Venus, that has been respectively visited by a Hayabusa mission and OSIRIS-REx mission. And after we have even comets, but comets, the main source of the comets are in the more outer part of the solar system. Some Jupiter family comets are close, they have a apohelium close to Jupiter, and the other ones are a little bit farther, but we will see afterwards. As I said, the composition of the asteroids varies, and actually we have at 3 astronomical units from the sun, we have what we call the snow line. So it means that all the bodies, or mainly the body that formed from the protoplanetary disk during the origin of the solar system, outside of this boundary, are more composed of icy or ice and organics, whether and in the other way around, actually in the closest part, we have asteroids that and bodies that are more rocky, composed by more rocky material. So they are classified in three big groups. There are many classifications, even more complex, but three main groups. So we have the stony asteroids, that they are the brown one, the ice group. Then we have which are closer to the sun. And then we have the carbonaceous object, which is rich in organics and volatiles and ice that are altered from the sun. And some of these part of these asteroids were able to arrive to the surface of the Earth as meteorites, carbonaceous chondrites, that are thought to be the most ancient, more primordial material of our solar system. And all of them could have or have metal, and in particular the closest one, and you see the gray part of metal. The good things of asteroids, if you want, and if you work on that, is that actually asteroids are named sequentially from the discovery, but they can be even named after alive people. All the naming on planetary surfaces are actually follow different routes, but if they are after some people, they are normally dead from at least 10 years, I think. Actually, the asteroids are from alive people, and you can even see here some of the people that has been part of this course, so many, so it's not so difficult to have an asteroid named after you, in particular, if you work on small bodies, but even on planetary geology in any case, so that you can see, for example, I have a good probability to be a primordial asteroid. And this makes sense since I am probably the oldest speaker of the entire winter school. Which are the processes that shape the asteroids? Actually, the asteroids are small bodies, so they have no inner they have no inner heat source, so they have no actually volcanism, except for the one that we have already seen during the second day of this course, which is Vesta, for example, that has his own volcanic activity, that could have had this volcanic activity, and even Ceres that has a cryovolcanism, as you have seen already. And when you have small bodies, you have no heat source at its interior, so it's affected actually from external processes. The most important one is actually the impacts. And here you see a model of how Messilia crater in Lutetia asteroid, which is an asteroid, asteroid belt, that has been hit by of 100 kilometer of diameter maximum, or a little bit, I would say 50 to 100 kilometer, and you see that these are the main processes. And so what you have to do when you make geological mapping of these asteroids is to date, if you want, relatively the events of the impact of the on the initial body. So, for example, to the right here, you can see this asteroid that is Massilia craters that is superimposed by other craters, this one, for example, or the North polar crater cluster here, that is superimposing this one. So it is possible, even on asteroids, to have an evolutionary history, which is an evolution of the impacts and the ejecta related to that impacts. And using the crater density that you have already seen, I think, in the second day of this course, we can even infer the ages of the different events. And here you see the ages of the initial body and the ages of the North Polar crater class, I mean the absolute model age that can be considered. Within the craters, you even have remobilized processes like this one that you see, 4, 5, and 3 that are actually granular flow, gravitational taluses, landslides that can be seen. So even in case in which you have small bodies with low gravity, you still may see some features that are typical gravitational feature. Among the asteroids, this is a kind of asteroid in which you see have a rocky aspect, but among the asteroids, we have even asteroids that are called I would say rubble piles. And if you see them, this is a near-Earth asteroid, so it means it's asteroids that intersects the orbits of the inner planets. So this asteroid that has been visited by Osiris-X, and you have already probably seen the seminar by Maurizio on that, you will see that it's actually made up of breccia, of different blocks and material like that. And actually, the mapping of these asteroids, as I said before, is at the beginning, you focus on the mapping of the craters and some linear features. Then you have the mapping of the mass movements, as you see there, that can be a remobilizing of the material that could be even triggered by the impacts themselves. Some low-bed deposits, that means some fluid material, and even for example, an example of a big eventually area, and the place where the Osiris-X have collected the material. Together with that, you can even add on these informations, the information is about the roughness of the units. So you have the smooth units and the rugged units. So if you see here, you can see how the map has been done on, or can be done on, this kind of bodies, and with quite simple, if you want, geological processes, even if when you have a superimposed crater, it's quite difficult to always understand the superposition, in particular in this breccia-like type of asteroids. Among the things that you have to map on asteroids are what we call linear features or lineaments that actually could be of different origins. Many of them normally are fractures, but they could even be grooves. That it's a generic terms that may be even some ejecta rays, for example, or chain of secondary impacts that can be visible on different kind of small bodies like this one. So here, for example, you see Eros and Lutetia, the body that we have seen before, with some of the lineament, and they are plot in stereoplots. We will see what stereoplots are afterwards. And for sure, to map this kind of things, you actually, it's much easier to map them directly in 3D with respect to map in a projection, cylindrical or conical or whatever projection, stereographic, that we have seen before. Since when you have a so irregular body, it's quite difficult in the projection to really understand the relationship between the features, in particular the features that cross-cut through the body itself. So this is, for example, the case of, for example, the case of Phobos, in which is actually the moon of Mars, one of the two moons of Mars, so which is not big enough, not so big, so it can consider a small body. It's characterized by an important crater that is called Stickney crater, as you see there. It seems like a eye of a cyclops in the body itself, and from that element you have some ejecta blanketing the surfaces all around, and you see even some color differentiation. And again, in the center of the image, you see the map, how it is, how actually it is the map, the lineaments of the map, and the grooves that I've seen that you see before, and the main features that normally are typical of this kind of bodies. And to the right, you see a study that aim to understand the relationship between the crater itself and the grooves, the lineament features. And this study to the right had the aim of understanding if these fractures were originated by Stickney, for example, crater, or other crater in the body, because when you form a crater, actually you form radial fractures all around the crater and some concentric fractures. So, and you have seen actually them even on Vesta, for example, these kind of grooves, the equatorial grooves that Alessandro showed you in the second day. So, so understanding the relationship between these fractures may help in understanding how they formed, and even in some cases the origin of the body itself. And actually these grooves on Phobos have different potential origin. They could be as I said, ejecta from the crater itself. They could be fractures that has been derived by a parent body that was destroyed, and then part of this parent body was captured afterward by Mars, becoming the moon Phobos, for example. This is a possibility that can be checked with the fracture arrangement. And then there could be even grooves that were formed by ejecta of impacts on Mars that reached Phobos, creating this kind of striation on its body. So there are many things that can be understood by the study of the fractures itself. And for example, relating these fractures with the composition, because if we have, for example, water-bearing minerals on the surface of Phobos that has been seen, for example, we may even infer that some of this material for forming Phobos is actually from Mars. I don't know if the grooves, but if they are associated together, it could be. So because of that, because we would like you to try the mapping of these small bodies, we will work on VuarGS afterwards with David, showing how these features can be mapped. So the grooves that you see here going through the body itself, their relation with the craters that you see there, eventually mapping the different craters, understanding how would be the different crater density, because you have different terrains with different crater density in function of when they formed. So this will be part of the first part of your tutorial. The second part of the tutorial will be on comets, and actually the comets can be subdivided in two main groups. I would say the short period comets, so it means the periodic comets, the period is lower than 200 year, and the long period comets that are the comets with a period which is longer than 200 year. So actually we can even think that the short period comets are the Halley comet. They are actually no Halley comet, but they are less beautiful. And since we see very faint tail, very small tails, whereas the longer it is the period, for example, Halley, which is still a short period comet, but has a returning period of 75 years, it's very nice to see it with beautiful tails. And Hale-Bopp, which is even not a periodical comet, so it came from far, very far, and it was seen by naked eyes with the two tails. So you see the ion tails, which are directed perpendicularly to the sun, and the dust tail that it's actually following the orbit, the white one. So, and why we have this kind of different behavior between the short period comet and the long period comet? Actually, the short period comet, some of them came from, most of them came from the Jupiter family comet or the Halley family comet. So it means that they go close by the sun every short period of time. For example, 67P that has been visited by Rosetta, and we will see it afterwards, has only 6 years of 6.5 years of period revolution. So it means that it goes close to the sun several times. So going close to the sun, we have all the sublimating material that sublimates, creating the tail. And then we have all the other material, like the organic or the rocky material that fall down on the comet, covering it. So actually, the comet destiny is to switch off after several passages on close to the sun, or eventually it can be even captured or destroyed by big bodies like Jupiter that destroyed the Schumacher-Levy comet, for example, or they can fall inside the sun and so on. The most beautiful comet, however, they have less, I would say, longer period of perihelion passages, so they are much more beautiful because they are not covered yet by inert material, and they come from the Kuiper belt, or they come from the Oort clouds. And the Oort clouds, it's actually the limit of our solar system, so the boundary of our solar system. And for these reasons, since they come from very far, they have a very eccentric, very elliptical orbit, even inclined, that can be even inclined, sensibly inclined with respect to the elliptical, I would say, orbital plane, or all the other planetary bodies. And here you see the different comet that has been visited so far by different missions. For example, the Giotto mission 1980 visited the Halley comet, and the 67P was visited by Rosetta missions, and the other deep space visited the Borrelly comet. So we know actually the nuclei of these comets, and you see them here in these images. So if you see these images, the Halley comet, you see that the nuclei is covered by a kind of sublimating atmosphere that is the coma, and from the coma, that is actually continuously, it's continually injected by sublimated material from outbursts that you see there. We will see afterward what they are. And from the coma you have, and from this sublimating material and the dust, you have the formation of the tails that we have seen before. So the comet that we know better, the comet nuclei that we know best, it's actually 67P, Gerasimenko, which was visited by Rosetta after 10 years of journey. And so because of the need of a gravity assist, so to use the gravity of the other body to reach this comet, it actually takes 10 years to reach the comet itself. And after the flyby Volutesha that we have seen before, we reached the comet in 2014 after, as I said, 10 years of journey. And you have to consider that a mission like that has at least other 10 years to be prepared. So in order to arrive to the object of the mission itself, we had to spend 20 years. So the mission sometimes is something that has been built up by some people, for some scientists, for the future scientists, okay? So I had the opportunity to be part of these missions from 2008. So when it was already launched and visited, as I said, a couple of asteroids, Stein and Lutetia. And here in August 2014, when we were some millions of kilometers away from the comet, it was possible still to see, if you see there, to see the sublimation. So the comet was sublimating. It was still quite far from the sun. So it means that the super volatile material were sublimating in that moment. So volatile material that sublimates at low temperature, like very low temperature, 70 Kelvin or something like that, like CO and CO2. When we approached the comet, we were able, actually Rosetta was able to orbit around the comet, and it was possible to see actually in very detail how the comet is in terms of morphology and geology. And it was even able to land there a lander which was called Philae. Here you see it's incredible how a comet is actually variegated, I would say, different in terms of morphology. You see steep cliff, terraces, circular features, blocks, smooth material, dark material. And actually the comet you see here is pretty dark because it's full of organic on its surface. And so it's really, really impressive how a comet could be interesting from a geological point of view, because actually a comet, it's the realm of sublimation. In order to understand the sublimation processes, you should go and study a comet, because everything that you see there, it's sublimation. Most of what you see is sublimation-driven surfaces. And if you want to study sublimation, it's very difficult to study it. You can study it, for example, in the Earth, in very on glacier, which are at high altitudes, in which you can see some sublimation feature. You can study sublimation on some polar cap or close to the polar cap of Mars, for example, some sublimation feature on particular material very close to the sun on Mercury, which is very close to the sun. But actually, all the features that you can see are sublimating feature. And all the circular features that you see here are actually no impacts. They have no elevated rims, they are irregular, and we don't see impact there because the sublimation is so strong that delayed any impact there. Actually, we saw a very small impact only on Comet 60P during the entire mission. So let's have a look on the material that we see on a comet nuclei. And if you see here on this image, you can see clearly that we have a kind of dusty material, smooth material, okay? Then we see some outcropping material, rocky-like material that creates actually outcrops. And then you see blocks and talus material. And at the base, at the foot of the rocky-like material, you see this kind of talus that is actually a gravitational talus, because even in the case of the comet 67P, which is a very low density material and which is 4 kilometers of diameter, we have a gravity that can lead to this kind of gravitational processes. By the way, I would say that the comet itself density is 0.8 grams centimeter cube. So if you would have the comet itself on our on one of our lake on the sea, you would see it floating. Okay, you would see a floating island of 4 kilometers of diameter on the ocean. Okay, this just to have an idea of the low density and of the comet itself, because it's even a high porosity comet. So it means that it's a porosity that is close 60%. So as I said, we see dust material, we see rocky material, we see talus deposits, and we see blocks. And the dust material is actually the effect that I've said before. And here you see the sublimating 67P that is sublimating between the two parts of the comet itself. You see the comet is made of a small body and a big body. The small body is called the head, the big body is called actually the body, okay? And in the neck between the two, you see the sublimation. So when we met the comet itself, we saw that sublimation, that it was in between the two lobes. And from the sublimation, we have that the material, organic material and dusty material float, and then afterwards fall down to the surface of the comet, creating this kind of dusty material. And that is covering the comet itself. And it's actually the mantle that in a longer period can switch off the comet after several perihelion passages. We were able to follow the comet even at perihelion passages. So going closer to the sun, we were able to see that actually the comet was sublimating everywhere. And we have a beautiful example of focused sublimation, and that are called outbursts. And the outbursts are actually formed in several processes, but for sure we were able to see one of them, and that was described by Maurizio on 2017. So here you see three images, okay? One in 2014, before the perihelion passage, then in 2015 during the perihelion passage, and in July, and then December, soon after the perihelion passage. And you see that in July, we had an outburst coming for the big lobe, okay? And you see actually the comet from far in July 2015, because when you are very close to the perihelion, the dust was so big, so important, that it was difficult for the satellites to maintain its its orbit around the comet. So we had to go farther from the comet and see it from far before approaching the comet again. And to the lower right here, you see actually how is the temperature variability on the comet close to the perihelion. The comet is actually orbiting around an axis which is cutting actually the neck. It's here on the neck, and we have a rotation around this axis with a period of 12.5 hours. And this kind of color here, you see the different temperature that experience the different regions of the comet during the rotation. And in this point where we see the outburst came from, in this point, you see that we have an announcement in only less than 12 hours of the temperature from, I would say, something which is 80 Kelvin or even less, to something which is 360 Kelvin. So we have a temperature difference which is impressive. And this kind of temperature difference create a lot of fractures by thermal stress on the comet itself. And through the fracture, we have that irradiation go through the fraction and may trigger sublimation and open the fractures. And through the triggering of sublimation and the opening of the fraction, you have the event of collapse. So I would say the gravitational events on the comet are actually triggered by are predisposed by the thermal effect of fracturing and triggered by the sublimation, at least in this case. And during this event, you have an example of a possible, actually, we had a sure example of an outburst. And here you see clearly this cliff here, and then the outburst and the cliff that has been actually cut here. exposing sublimating material. The bright material is ice. And this creates the outbursts. And here you see actually the effect of a landslide, if you will, a rockfall on the comet. And you have to consider that this cliff is around 100 meters of elevation. We have even some other focused events of sublimation in some places. And if you see here the big lobe, you see that we see different circular features. And we see among these circular features, we see an example here, which looks really like a pit. It's a pit of 100 meters of diameter and more or less the same of depth. So and if you look at there and you work a little bit on the images, you see that you have focused sublimation again inside the pit itself. And even you see that this kind of pit could be in some case related to the other circular feature that you see here. Here you see a very faint pit. Here you see a kind of collapsed pit. So there is a kind of trend evolution from this case to this case. And the idea is that at the beginning, we may have a sublimating material underneath the surface. And this is because we may have more super sublimating material, so CO2 there. And because of the thermal waves reaching that part, you have starting the sublimation. Through the fractures, the material, sublimating material can find its way outside the surface of the comet nuclei, the fracture that we have seen already, the fracture that can be formed by thermal stress. And so we have that the underground cave enlarged up to the collapse of the roof, forming the pit. From the pit walls, we have enhanced sublimation, and even from the collapsed material underneath. The sublimation of the given wall can create a retreat of the wall, forming this semicircular feature. So this is actually the interpretation. So at the end, all this material, this feature can be mapped here. And here we see an example of a detailed map of a given part that can be done just on the images and on mosaics of the image. So you can see breccia-like diamicton deposits, you can see talus, you can see the outcropping material, you can see different lineaments of fractures, because we have said we have many fractures, niches, and even some crest features. And as these ones, some of them can be actually kind of dune-like features that can be created by sublimating outbursts that are parallel to the surface themselves. So very, very particular polygons. When you have to work on the comet, below the comet, you can even have a global map like this one. So you see talus deposit, cliff, and smooth deposit, and so forth. But actually, when you project it, even if it's quite difficult, it was possible to project all this material, it's really difficult understanding where the relationship between the different units. For example, this part is the big lobe, this part is another part of the big lobe, and here in the center, we have the small lobe, and all around we have the neck. So it's really difficult to understand the relationship between the unit looking at the projected part. So the best thing is to map, to work directly when you have to do some global mapping on the shape model, on the 3D model, like here, in which you see clearly the relationship between the different units. One of the main problem of the comet was understanding if the two lobes were formed by aggregation after a catastrophic impact, like in this case to the right, or could have been formed from primordial cometesimal in the protoplanetary disk. And in order to understand it, it is important to understand the internal part of the comet nuclei. There was an experiment for understanding the internal part of the comet nuclei, which was a rather experiment from the lander, which was Philae, that has to communicate, if you want, to the orbiter through the radar, and the penetrating radar wavelength would have had the possibility to understand the interior of the comet itself. So if we found a very interior with different kind of pieces, it's for sure we would have a catastrophic collision and reaggregation. However, because the Philae went bounced of the comet and went in a shadow region, the solar panels were not powered anymore, and it was problematic to use that kind of experiment. So we used actually the observations. And if you see on this image, you see that you have a staircase pattern here, for example. Okay, this staircase pattern are very similar to what we normally see on other planetary bodies, even the Earth, in which we see stratification. So on this comet, we can see stratifications and terraces. And through stratification, it is possible actually in the arrangement of the stratification to understand even part on the inner structure of the comet itself. And here you see that the terraces are actually many on the comet. You see the layering here in this wall, layering here, terrace here, another terrace here. You see a step like terraces here, okay? So every plane here of the terrace is a strata plane. So it is possible to measure them in 3D. And actually it was, this was done. And if you see here, you see all the vectors that are perpendicular to different kind of stratification. And you can, if you cut the comet through, you will see the shape of the comet and how are all the stratification all around the comet, okay? And it looked like actually that we have envelopes, you see, envelopes of the two bodies together. So probably the two lobes are only two and were aggregated after the stratification was in place. This was a kind of surprise because this kind of stratification was the first time seen on comets, and it was not supposed to be there. Because if this stratification formed primordially, we should have a method, I would say a process that form stratification from the protoplanetary disk. And we should have had quite an homogeneous protoplanetary disk with different regions so that you may have an aggregation at a given point and the stasi of aggregation at another point and so forth, creating a potential stratification. This could be a possibility, but was not foreseen before, and we have no model to show it yet. Another possibility is that stratification could be an evolutionary stratification afterwards through thermal waves. We don't know actually, but we know that stratification can be used for understanding the interior of the cometary nuclei. And in particular, we can use the attitudes, the orientation of the stratification in function of the gravity vector. And indeed, if we have two lobes, we would have a total gravity vector that could be the contribution of the gravity of the two lobes, and a gravity vector consider a single lobe, okay? So in this case, we would have this gravity vector for the big lobe, and for this point, this could be the gravity vector of the small lobe. And this is the total gravity vector. So we can relate the orientation of the stratification with the gravity vector and see the misfit between the gravity vector and the orientation and the perpendicular, if you want, of this, the perpendicular to the strata, in order to see if the gravity has affected the formation of the strata or not during the production of the layer stack. And if you see on this diagram, you see that this is the misfit between the two angles for the total gravity vector and for the vector of a single lobe. And you see that actually we have a smaller misfit between the observation of the strata and the gravity vector if we consider the single lobe. So it means that this stratification formed before the two lobes aggregated together, probably in a very early part of the evolution of the solar system. And here you see to the right the interpretation. So we have this kind of stratification that go up to 500 to 800 meters of depth on the small lobe, and on the big lobe we have lost some of the stratification in between, probably during the joining of the two lobes. We would have pieces that were broken and went away, okay, and the two lobe stratification formed separately, and then we would have had the joining of the two materials. So this during the second practical activity, we will go through the Comet 67P, look at their stratification, the relationship with the gravity vector in 3D again, because this is another case in which we need a method for working in 3D. And for sure, ArcGIS is one of the most promising tools that can be used for understanding and making geological mapping and structural analysis like this one on small body. So now, actually, I've finished. If you would say, I would leave the stage to David, that will introduce you at the beginning the ArcGIS software, and after all, he will show you the activity, some of the activity that can be done with that software on small bodies.